All right, welcome everyone to today's TCS Plus talk. I'm today's moderator for the talk, Gautam Kamath, and I'm representing an awesome team who runs this. TCS Plus is a weekly or bi-weekly seminar on theoretical computer science. I'll remind that the next talk we have is next Wednesday by Ronit Rubenfeld, which should be really exciting. So stay tuned for that. But today we're really lucky to have Nicole Wein speaking to us. Nicole is currently a postdoc at DIMACS. She recently completed her PhD at MIT. And yeah, she's done some really awesome work on graph algorithms, lower bounds in a variety of different areas, which are all really cool, trying to understand questions such as how can algorithms cope with changing data, and what information can algorithms extract from a graph in only linear time. So today she's going to in particular be telling us about online list labeling, an exciting result that was in this box that breaks the log squared n barrier. Without further ado, Nicole, please take it away.
Thank you for the introduction, and thank you to everyone for being here. So today I'll be talking about the online list labeling problem and breaking the log squared n barrier. This is work by 6 authors who are here in alphabetical order. So Michael Bender, Alex Conway, Martin Farich-Colton, Hanna Komlosh, and Bill Kuzmal. And let me also mention that right now, half of these authors are on the faculty job market. In addition to me, Alex Conway is, and Bill Kuzmal is. So let me get started. So these slides were made collaboratively among the 6 of us. Okay, so first, let me introduce the problem. So this is the online list labeling problem, and this is a data structures problem. And the goal of this problem is to maintain n elements in sorted order in an array of size m, where you can think of n as being at most m over 2 for some value of 2. Just think of the array as being a constant factor bigger than the number of elements in the array. And we have an adversary who is inserting and deleting elements from the array. And as the adversary inserts and deletes elements, as the algorithm, we are allowed to move some of the items around in the array to make room because we need them to always be in sorted order. And our goal in this problem is to minimize the number of elements that are moved per insertion deletion. Okay, so that's the problem. One way to think about this problem, if you wanted to explain it to a child, let's say, is you could say, imagine you're a librarian and you would like to store some books on a shelf in alphabetical order. And you can imagine 2 different types of libraries that you might have. One would be a library with no gaps between the books, and the other one would be a library that has gaps between the books. And the idea is that if we don't have any gaps and we need to insert a new book, we might force many books to move around. And so we may want to preemptively leave gaps in our data structure to allow for new elements to arrive. Okay, so this problem was first introduced in 1981 by Itai, Konheim, and Rhoda. And throughout the 80s and 90s, it was kind of reformulated and rediscovered a number of different times using different names. And over the years, it has also found a number of different applications. So here's a list of some of the applications. Probably the most well-known one is cache-oblivious B trees. And the result that I'm going to be describing today has immediate improvements for the bounds for cache-oblivious B trees. And there are also a bunch of other applications that span between theory and databases and other areas in practice. Okay, so now let's talk about what is known about this problem. So in the first paper to study this problem, they showed an upper bound of log squared n. This was Itai, Konheim, and Rhoda in 1981. And what they showed was that given an adversary inserting and deleting elements, we can always guarantee that we have an algorithm that moves around only log squared n items per insertion deletion. And they first proved this in an amortized sense, and it was later improved to be worst case by Willard. From the lower bound side, it has been known since 2013 that there's a lower bound at log n, and this is by Bulanek, Kotsky, and Sachs. And so the question that we're asking here is, can we close this gap? What is the correct answer between log n and log squared n? So from the upper bound side, since 1981, 40 years ago, this upper bound has remained unimproved. And from the lower bound side, there has been some work for specific cases. And by specific cases, I mean for specific classes of algorithms. You can show a better bound than log n. So to tell you about these specific classes of algorithms, let me first just kind of get our hands on the problem a little bit and think about what is a natural strategy that you could use to solve this problem. So one very natural strategy would be the following. When an interval becomes too dense, so an interval of the array has too many elements in it, let's just rebalance those elements evenly over a wider interval. So you can see this element is being inserted, and let's say this particular interval became too dense. Now we're just going to go ahead and rebalance everything evenly over a wider interval. And you'll notice two things about this strategy. One is that it is deterministic, assuming that you pick your criteria of too dense deterministically. And the other one is that it is so-called smooth. And by smooth, what I mean is that the only type of rebalances that are allowed are evenly spaced. So whenever I'm moving elements around, I'm choosing an interval and evenly spacing everything throughout that interval. And it turns out that for both of these strategies individually, there are tight lower bounds. That is, we know that log squared n is the correct answer for deterministic algorithms by Dietz, Cypheres, and Zhang. And for smooth algorithms, we also know that log squared n is the correct answer by Dietz and Zhang. And so the question that we're really asking here, when we're asking, can we close the gap between log squared n and log n, is can we use the power of randomization and uneven rebalancing to improve over log squared n? And at least a few groups in the past have conjectured that log squared n should be the correct answer for general algorithms. And for most of the time that I spent working on this problem, I really thought that log squared n should be the correct answer. And one piece of intuition is that it's kind of difficult to initially see how uneven rebalancing could possibly help us here. If I'm rebalancing items in the array unevenly, I'm creating some sparse areas and some dense areas. And then the adversary could kind of target the dense areas. And so why would this help? Well, it turns out that that intuition is incorrect, and you can actually get an algorithm that's better than log squared n using the power of randomization and uneven rebalancing. So our main result in this paper is that you can get an algorithm for this problem with log to the 3/2 of n expected cost per insertion deletion. So going back to this picture, now we have a gap between upper and lower bounds of log to the 3/2 n and log n. And you'll notice that our result of log to the 3/2 n is by necessity both randomized and non-smooth. Okay.
Nicole, I just want to ask,
yes.
Is that in like a worst case expected sense, or is it amortized in any way or not?
It is amortized. So it's like for each insertion deletion, it's in expectation. So like overall, it's amortized. It's not with high probability, which would mean that it would be like worst case.
Okay. Sure. Sorry, let me just ask one more question to see if I can clarify in my head. Like, is the distribution for individual inserts and deletions, will they all like sort of individually be concentrated around that log 3⁵ n, or is it like, are there some which will sort of with high probability be even like linear cost or something, but it just is evened out by other ones being in expectation cheap? Like are the distributions sort of like the same for each insertion, or are they very different in terms of their expectation?
Yes, so we can show that for every individual insertion, the expectation is log to the 3/2.
Cool. Okay. Yeah, that sounds nice. In my head, that's what I was calling worst case. Cool. Thanks.
So let me now make two observations that I find interesting about this result. One of them is that it turns out that randomization and uneven rebalancing only help when your array is linear in size compared to the number of elements in the array. It has been previously known that if your array is actually way larger, if it's like a polynomial compared to the number of elements in the array, it turns out they're matching upper and lower bounds of log n, and these are deterministic and smooth rebalancing. So somehow there comes a time when you make the array smaller and smaller where suddenly you get the benefits of randomization. The second observation that I want to make is, isn't log n kind of an unusual number? So you might think that if you can break log squared n, then probably the correct answer is going to be log n. But it turns out that there's actually some evidence to suggest that maybe log to the 3/2 n could be the correct answer. And in particular, log to the 3/2 n is tight for a particular natural class of algorithms. So let me now tell you about this class of algorithms. This class of algorithms is what are called history-independent algorithms. And this idea of history independence is going to be like one of the central focuses of this talk. So this definition will be very important also later on. So in general, the definition of history independent is that a history independent algorithm is one such that if you look at the current state of the data structure, it reveals absolutely nothing about the history of past operations, besides the fact that you can see the items that are currently present. So by looking at the current state of the data structure, I don't know anything about what order the adversary inserted them in, what deletions were done along the way, et cetera. And this is an idea that has actually been widely studied for a number of different data structures. And with this research, the goal is often to show that, okay, we have like a hash table or something, and the goal is to say, can we match the state-of-the-art bounds while also getting this additional property of history independence, because it's kind of a nice property. So now let me zoom in on online list labeling and what history independence means for us. So history independence for us means the following. It means that the distribution over occupied slots in the array depends only on the number of elements currently present in the array. So first of all, this distribution is with respect to a randomized algorithm, right? Because we're only now considering randomized algorithms. So we have a distribution over which slots in the array are filled. And the claim is that, or the definition is that the occupied slots only depend on the number of elements currently present. They don't depend even on the identity of the elements. And this is a little bit of a not very important caveat, but in this problem, the elements that I'm labeling with letters here are not like actual elements with identities, because in the problem, the adversary is just saying, I'm going to insert at like right after the ith element currently in the array without specifying an identity of an element. It's just easier to see that way. So in any case, you can just think of history independence for our problem being that the distribution of occupied slots only depends on the number of elements currently present, not the identities of the elements and not the history of what happened in the past. Okay, so our result now in this context is that, first of all, the upper bound of log to the 3/2 n is history independent. And additionally, we also show a lower bound of log to the 3/2 n for history independent algorithms. So if you restrict your attention to history independent algorithms, we know that the correct answer is log to the 3/2 n. And I also would like to note that history independent algorithms have been studied in the past for the problem of online list labeling, and there was an upper bound of log squared n, that is, this algorithm by this list of authors in 2016 matches the state of the art for the upper bound that was known at that time, and additionally has the property of being history independent. Okay, so now what I would like to point out is, I would say, the most important one single key point in the whole talk, which is that previously history independence was viewed as a desirable property to achieve in its own right, like for some sort of security guarantees, where we're saying, if you look at the current state of the data structure, you don't get any more information about what happened in the past. But in contrast, in this work, we're actually using the property of history independence as a tool to achieve a faster algorithm. So you can think of this work in a different way as like a proof of concept that this property of history independence can be actually useful in making algorithms faster.
Is this the first work that uses this history independence for any purpose besides security guarantees, like at all?
As far as I know, yes.
No, that's very cool then. Thanks.
So to be a little bit more detailed about why history independence could be important and useful for getting a faster algorithm, let me kind of give you a preview of conceptually what's going to happen later. So why is history independence useful for an upper bound? And the short answer is that history independence is all about hiding information from an adversary. So in particular, in prior work, when they cared about security, what they were saying was, by observing the current state of the data structure, some malicious adversary cannot deduce some extra information about the history. Now, on the other hand, for speed in our work, we're saying the exact opposite. We're saying that by knowing the history of insertions and deletions, the adversary cannot deduce the state of the data structure. That is to say, the adversary, of course, knows the history of insertions and deletions because they're the ones doing it. But even though they know the history, the adversary cannot deduce anything about the current state of the data structure. And so this is helpful because then the adversary cannot exploit the current state of the data structure to make it slow. So that's kind of the conceptual idea of what's happening and kind of a preview of what will be in the future. So let me now go into more details, in particular about the list labeling problem and the algorithm. So in the rest of the talk, I'm going to be talking about the log to the 3/2 algorithm. And I'm going to, for this talk, be ignoring the log to the 3/2 history independent lower bound. So to understand this algorithm, you first need to understand the classical solution from 1981, which achieves log squared n. So let me first show you how the classical solution works. Okay, so here's how it works. First, what we're going to do is partition the array into nested intervals. So on the top, we have an interval representing the entire array, and then one down, we've split that interval into 2 pieces, then 4 pieces, etc. And we're going to be maintaining a particular invariant over the intervals that we've divided the array into. And the invariant is going to be the following. So it's an invariant about the density of each interval. And the density of an interval is simply defined as the number of items currently in that interval divided by the size of that interval. And so what we're saying is that the ratio of a child interval to its parent is not going to be too big. It's only going to be like 1 + 1 over log n. That is to say, we're forbidding the scenario where we have some parent interval, and then when you look at its 2 children, one of them is super dense and the other one is super sparse. We're saying that that cannot happen, and in fact, the density of the children has to be about the same as the density of the parents. Okay, so now what I would first like to convince you of is that this invariant, actually, if we're able to satisfy this invariant, then we actually have a valid solution to the list labeling problem. So in particular, what I mean by that is we can analyze the density of each of these intervals. So let's consider the densest possible thing that could happen. On the top interval, we know from the definition of the problem that the density is constant. When we go down to the next interval, you can see by the invariant that the densest possible thing we could have here would be to multiply this original density by 1 + 1 over log n. And then you get another factor of 1 plus 1 over log n as you go down the tree. And the point here is that when you do this log n times, you get the density of an interval on the very bottom to be like 1 plus 1 over log n, all raised to the log n, which is a constant. And so we can say, indeed, at the bottom level, there are enough slots in the array for the amount of items that we wanted to put in that slot. Okay, so the point here is just that if we're able to maintain this invariant, then this is actually a valid solution to the list labeling problem where we have enough slots for all the items we would like to store. Okay, so now I need to tell you how you maintain this invariant. And the way that you maintain this invariant is very simple. We are just saying, okay, if the invariant is ever violated, let's just evenly spread all of the items over the parent interval. So in particular, here, let's say we're looking at this particular interval and the invariant is violated. You can see that indeed this interval is very dense and its parent interval is sparser. And what we're going to do is just simply look at the parent interval and spread all of these items out evenly. Okay, so that's the entire algorithm. So in summary, we're saying partition the array into nested intervals. We have this invariant about the relative densities of parents and children that we would like to maintain. And we're just saying when an interval violates the invariant, just spread everything out evenly, so that we're now resetting the density of the child to be exactly the same as the density of the parent. So now let's see where these log squared n bound comes from. So the source of the two log factors is number one, we have log n different levels in the tree. And number two, we need to calculate the cost of maintaining the invariant at each level. So in particular, we can say every rebuild of an interval of size s actually requires s over log n insertions deletions of the adversary. And the reason for this is because when we spread all of the items out evenly and do a rebuild, the density of the child is set to be the density of the parent. And in order for the invariant to then be violated in the future, we need for the density of the child and parent to have their ratio gone to 1 plus 1 over log n. And so that means that we need to insert a 1 over log n fraction of new elements into this interval in order to violate the invariant. So the result of this is that the cost is s, because s is on the numerator, because when we rebalance an interval of size s, we're paying s. And then on the denominator, we're saying that we only do this once every s over log n insertions and deletions. And so this comes out to a cost of log n, and then another log n for each of the levels. Okay, so this is roughly what the analysis looks like of the classical solution. And now our goal is to be able to improve this to log to the 3/2. And the way that I'm going to describe this is kind of like an iterative approach where we say, let's try to fix it in a particular way, and then something goes wrong, and then we fix that, and something goes wrong again, etc. So the first simple idea that we're going to try is let's just try to balance everything less tightly. So let's just have an invariant that's less stringent, and that will allow us to rebuild less often and have less cost. So what I would really like is to have this new invariant where the density ratio between the child and the parent is going to be like 1 plus 1 over square root log n. And the reason I want this is because if you do the calculations from the previous slide about the cost, what you're going to have is now that the cost of maintaining the invariant becomes square root log n at each level, so that you get a final cost of log to the 3/2 n, which is what we want. Now, there's a large problem with this approach, and that problem is that some intervals may overflow. And so in particular, you'll recall the density calculations that we did for the classical algorithm, and we concluded at the end that there were enough slots for all the items we wanted to insert. But if you do the same analysis with square root log n instead of log n, then what you get at the end is that the density of the final interval is 1 plus 1 over square root log n, all raised to the log n. And this is going to be super constant, which means that there's not enough slots for all the items. So this is not even a valid algorithm in the first place. Okay, so that's the problem that we're dealing with. And now what we would like to do is address this problem. So in particular, the problem is that we have these very dense regions that will overflow if we don't do anything about it. And so we need to specifically handle the dense regions. So to handle these dense regions, my claim here is that there's kind of still hope, because you can claim that actually not too many intervals overflow. Only like a 1 over polylog n fraction of the intervals actually experience overflow when you use this new invariant of 1 over square root log n. So let me convince you that this claim is true. So my claim is that when I use this new invariant, which is 1 over square root log n, I'm going to experience some overflow, of course, but not too often. Only like a 1 over polylog n fraction of the intervals are going to overflow. And the proof idea is the following. So let's consider a random sequence of nested intervals in the array. Now we can consider the densities that occur on each of these intervals. And in particular, these densities form a random walk. So you can see that if I look at a parent interval and I look at its two children, the average of the densities of the two children is of course going to be equal to the parent. And so this is an unbiased random walk where with 50% chance you're increasing the density and 50% you're decreasing it by the same amount. And the step size of how much you're increasing or decreasing the density is determined by this invariant, which is that the densities only differ by like 1 over square root log n. Okay, so we're doing this random walk all the way to the bottom of the tree. And we can now use a fact about random walks, which is that if I take a random walk for k steps, with high probability, I'm going to be of distance about square root of k from the origin. So in this particular circumstance, I'm taking a random walk of length log n, which means that I expect to be about square root log n from the origin when I get to the bottom. And in particular, each of these step sizes is only 1 over square root log n. And so these square root log n's actually cancel each other out. So to look at the calculations explicitly, we're saying with high probability, the density on the bottom level is square root log n because of the fact from random walks that we expect to deviate square root log n steps from the origin. And another 1 over square root log n factor because that's the step size in the random walk. And so when you calculate this, you then get constant. So we're saying with high probability, when you get to the bottom interval, it's only constant density and therefore it does not overflow. And so the upshot is just that only a small amount of these intervals overflow because we chose this sequence of nested intervals at the beginning randomly. And in particular, the high probability that we're talking about is with respect to the number of steps in the random walk, which is log n. And so we're getting that at most a 1 over polylog n fraction of the intervals experience overflow. Okay. So now that we've established that we don't experience overflow too much, let me say how we still have to deal with the overflow. And the way that we deal with the overflow is a simple solution where we're just saying, okay, whenever an interval gets too dense and is at risk for overflowing, let's just revert back to the log squared n solution that we already know works for that interval. So in summary, what we have here is the following picture. We're saying, okay, here's our array, and the vast majority of the array has cost log to the 3/2 n to insert into, But there are some small parts of the array, in particular a 1 over polylog n fraction of the array, which is getting too dense and at risk for overflow. And on this part, if the adversary chooses to insert there, we're going to have log squared n cost. Okay, so this is starting to look somewhat promising, but there's a big problem still here, which is that we're still vulnerable to the adversary. So in particular, if the adversary knew where all the dense regions were, they could just keep on inserting over and over into the dense regions, and our cost would still be log squared n. So it appears that we may have made like no progress whatsoever from the classical algorithm.
Nicole, one question here. At this point, is the algorithm still deterministic and smooth?
Yes, the algorithm is still deterministic and smooth.
Got it. Thanks.
Okay, so the final step here is to fix this problem where the adversary can exploit the dense regions of the array using the ideas of randomization and history independence. Okay, so let's kind of zoom in on the two problems that actually are occurring here. So it turns out there are like two distinct problems, and both of these problems result in the adversary knowing the location of the dense regions of the array. So the first problem is that the adversary can actually create dense regions of the array, because the adversary is the one who is performing all the insertions and deletions. So if the adversary inserts a bunch of stuff at the same place and the algorithm doesn't respond fast enough to spread it out, then the adversary has successfully created a dense region and therefore knows where it is. A second problem, which is distinct from the first problem, is that the adversary can find dense regions, even if the adversary did not create them. And what I mean by this is that the algorithm could have, in the algorithm, it could be creating some dense regions. That is to say, the adversary could know something about how the algorithm is working and that it's more likely to create dense regions in some parts of the array rather than others, and then the adversary can then kind of predict where the dense regions are going to be, even if they didn't create them explicitly. Okay, so it turns out that both of these two problems are going to be fixed essentially with the idea of history independence. So first of all, let's look at the solution to the first problem, which is that the adversary can create dense regions. And so the question here is, why does history independence prevent the adversary from creating dense regions? And the answer to this question is essentially just by definition. Because we know, by the definition of history independence, that the distribution of occupied slots in the array depends only on the number of elements currently present. And so the adversary can't do something clever to create some dense regions because the current state of the array actually is completely independent of whatever the adversary decided to do. Okay, so if we actually succeed in having an algorithm that does have the property of history independence, then we don't ever have to worry about the adversary being able to create dense regions, because the current state of the data structure is completely independent from the behavior of the adversary. Now, for the second problem, it essentially is also solved by history independence, but there's also kind of an extra little technical ingredient here, which I'm not going to dwell on too much. And the extra technical ingredient is called the random shift. And what we essentially do is like insert a random number of dummy elements to the beginning and end of the array. And the idea of this is that like somehow if the adversary could predict where the algorithm is going to make dense regions, then this random number of elements that we're inserting kind of creates some uncertainty about where these spots actually are in the array. Okay, I can elaborate more on this later if you're interested. It's actually not even clear if the random shift is essential to the algorithm, but it certainly makes it easier to analyze. Okay, so Now we would like to have an algorithm that is history independent. And we've seen that the property of history independence will help, but we need to actually have an algorithm that has this property. And in order to get this algorithm, we are building on prior work. So as I previously said, there is a log squared n history independent algorithm that has been known since 2016. And we use this as the starting point for our algorithm. And this algorithm kind of conveniently plays well with everything that I've talked about in the past because it actually has a very similar structure to the classical algorithm. Now, I won't go into full detail of what this algorithm is, and I'll be happy to elaborate later. But essentially, the idea of this algorithm is that it's similar to the classical algorithm, except instead of rebalancing things exactly evenly, like we did in the classical algorithm, we're actually going to include some randomness in the way that we rebalance things. Okay, so now I'm going to just summarize all of the ingredients, which I've mentioned all of them in the past, that go into this log to the 3/2 algorithm. So the first ingredient is this log squared n history independent algorithm from prior work. And we also use this extra ingredient of the random shift that I briefly mentioned. And we additionally use this idea of balancing the densities less tightly, which was the very first idea that I mentioned at the beginning, where in this log squared n history independent algorithm, they still have this invariant about the density of the parent versus the child. And we're again saying, let's balance these densities less tightly so that we can rebuild less often, and this speeds up the algorithm. But we still, again, run into the problem of having some overflow because the new invariant allows for overflow. But as we showed before, the number of intervals in the array that do experience overflow is rather small. And so for these particular intervals, we can revert back to the log squared n algorithm that's given by this history independent algorithm. And these are really the main 4 ingredients of the final algorithm. It's not really too complicated. It turns out that these 4 ingredients give you actually an O tilde of log to the 3/2 n. So there's some log factors in there. And there's an extra ingredient which allows you to remove those log factors. And the extra ingredient is basically, instead of just classifying parts of the array as either dense or sparse, you kind of have this smoothly varying density thresholds. Okay, so lastly, I would like to then recall that we also show a matching lower bound for history independent algorithms. And let me now move on to telling you about a couple of open problems. So first of all, the main open problem is now closing the gap between log to the 3/2 of n and log n. And so you can ask the question of, does our history independent lower bound extend to all algorithms? And there's kind of different intuitions you could have about this. Maybe it doesn't extend because history independence is it seems like an expensive property to maintain. On the other hand, maybe it does extend because history independence is good for hiding information from the adversary. We don't know. But if there is a faster algorithm than log to the 3/2 n, then it must by necessity be randomized, non-smooth, and have the property of being history dependent. So now let me zoom out a little bit more and say an open question that's more general, which is that in this work, we use this property of history independence to defeat an oblivious adversary in the problem of online list labeling. And the question is just, is this more widely applicable? Can other data structures use this idea of history independence also to defeat an oblivious adversary? Okay, that's all that I have for you today. But I'm very happy to stay for a while and answer any questions that you have.
Cool. Thanks a lot, Nicole. This was an excellent talk. Yeah, are there any questions from the audience? I'll start by asking, I guess, like you're hinting at like this question here, this last question. Do you have any results in this direction or investigation that you're willing to share right now?
Not really. I think of it as an open-ended question. I don't know what good candidates would be for this.
Sure. Another question I was kind of wondering from the start was, again, I'm a bit naive about online algorithm, but are there any connections between this problem and the K-server problem?
I have no idea. That's a good question.
Sure. Yeah, because it just somehow feels like both of them, again, I know little about either of these problems, but it feels like maybe you need to plan ahead and picture which regions are going to be served or something like that. I don't know. I was just curious about if anyone had looked. Are there
I'm not sure.
Questions from the audience? So I'll, in a second, stop the recording in case anyone wants to ask anything else. I'll remind that next week we're looking forward to a great talk from Ronit Rubenfeld. Cool. Thanks a lot for coming, and we'll see you next time.